Welcome to 6.5. This is going to be the last section in Chapter 6. We have really zoomed through Chapter 6. Remember we went in 6.1, similar polygons. Let's just remind ourselves, congruent polygons are same shape, same size. And then similar polygons are same shape, proportional. That's the key there, proportional size. And then we looked also at 6.4, different theorems to be able to prove that two polygons, in this case in particular, two triangles are congruent with each other. So angle, angle, side, 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 and side, angle, side. So those are theorems that we can use to prove that two triangles are similar. Now, applying those principles is really opening things up here when we use the triangle proportionality theorem. And because we can prove, we don't have to actually prove it now, but because we can prove that when we have two lines that are parallel within a triangle here, we can prove that this right triangle is similar, I almost said congruent, but is similar to this larger triangle. Therefore, we can do all kinds of really cool proportions. And it's really simple, actually. Remember proportion? Well, first of all, ratio is two numbers related to each other through division. And a proportion are two ratios that are equated to each other, set equal to each other. And so watch how simple this is. Once we know, and remember the foundation of this is that these two lines are parallel. So please mark those two arrows on your notes real nice and clear, because none of this would be true unless we know for sure that these two lines are parallel. But once we know that, then we can say, and let's see, how do I want to do this? Okay, then we can say, notice green over pink, so green over pink equals blue over orange. So this proportion here, I can obtain that by moving this over, green over pink, and then really kind of put an equal sign here, equals blue over orange. See how that works? Green over pink equals green over, what did I say? Green over pink equals blue over orange. All right, so for example, let me show you, apply that to a particular situation. Here we have a triangle, and there's another line on the inside that is parallel to it. And yes, if it was a mid-segment, going from midpoint to midpoint, then that would be parallel. But it does not have to be a mid-segment. All it has to be is just parallel to each other. And in fact, we know for sure that this is not a mid-segment because 4 does not equal 6, and so obviously this is not the midpoint. But as long as I know that these two are parallel, then in order for me to find this length here of x, it's super dog easy. All we do is say x over 9 equals 4 over 6. See how easy that is? And once we have that, so once we have that proportion, x over 9 equals 4 over 6, then we can cross multiply, as you know, and say 6 times x equals 4 times 9. 4 times 9 is 36, so 6x equals 36. Divide both sides by 6, and therefore x equals 6. That was easy, wasn't it? Didn't have to do many calculations at all. And notice that so what I did was I just put a fraction bar there and said x over 9 equals 4 over 6. I could have, let me erase this here, I could have swiveled this thing around, let's do it this way for example, and put my fraction bar over in this direction and said 4 over x equals 6 over 9. and that's going to give me the exact same answer when I cross multiply. It won't give me the same proportion, but once I cross multiply, it'll give me the same thing. So, for example, let's do that. Say 4 over x equals 6 over 9. If I was to cross multiply that, I'd get 6 times x. Whoops, I'm sorry, I don't see that too. I'd get 6 times x equals 4 times 6, which is 36. That's the exact same thing that I got before. So isn't that cool? It really makes things easy to be able to determine missing lengths here. Again, it's all built though upon knowing that we have to know that these two lines are parallel. Once they are parallel, then it's very easy to create a proportion to be able to find one part of it. The other theorem that you have here is really just the converse of what we were just saying. What we said was, if these two lines are parallel, then we will have a proportion like this. So here, we could have put pink over orange equals green over blue. That could have been our proportion. Or we could have switched around like this and said orange over blue equals pink over green, or we could have switched it over like this. Any of these options will give us the same equation after we cross multiply. Okay, that's what's so neat about these things. So again, what we said was, if these two lines are parallel, then we can create this proportion. The converse, remember that is switching. The converse is saying, if these segments are proportional, then these two lines are parallel. In other words, we can check to see if these are proportional, and if they are, then that is a proof that these two lines are parallel to each other. The contrapositive, remember back in chapter 2, contrapositive means you take the converse and you negate it. And so here we are, first we take the converse to get here, and then we negate it, meaning it's saying that they're not proportional. If they're not proportional, then we know for sure that they are not parallel. Okay. Let's do one more example from the textbook in order to get you ready. And actually, you're not going to have a problem like this in the notes, but just to show you that if you wanted to determine whether or not these two segments are parallel with each other, then you would do a proportional. You could measure is CB over BA, is that equal to CD over DE? And they give us measurements here. They first calculate what is this one, CD over DE, and that gives you this ratio, and then they calculate CB over BA, and that gives you this ratio, and once you simplify them, you see that these are not the same ratio, and therefore these lines are not parallel to each other. Okay, so that was, again, the converse of what we had done before. We first said that if these two lines are parallel, then the segments here will be proportional to each other. But what we just did was said that they are not proportional to each other, therefore these two lines are not parallel to each other. Okay, so you are ready now for what's here in the notes. And so notice they're asking us for YZ. So let's call that X. This length right here is X. And you can set this up however you want to. Not really however you want to, but there's lots of ways to set this up. But wait a second, before I jump in and try to make a proportion, we need to make sure that these two lines, these two segments are what? Parallel, right? And yes, indeed they are. That's what these little arrows here mean. These two lines or segments are parallel, so now we're free to create proportions. So you could say either 35 over x equals 44 over 36, or you could flip it upside down if you wanted to. Let's say 36 over 44 equals x over 35, or let's erase this here, and you could flip it this way if you wanted to, and you could say, let's put an equal sign here, 44 over 35 equals 36 over x. Okay? Or what I would probably do, because I don't know why, but it just makes me more comfortable. I like putting the x up in the top left. We could also say that if x over, or we could say that x over 36 equals 35 over 44. So now I have my x, that's the variable that I want to find, and I cross multiply. So I'd say x times 44 equals 36 times 35. And then you'd be able to solve for x. But you see how flexible and adaptable this is. And it really is fun to be able to so easily be able to, well, I mean, you know, mathematical fun. I'm not saying like ski down a mountain kind of fun, but it is pretty neat. Once we know that these are parallel, that really makes it, that is the key that unlocks these problems. And you know what? I said that we were not going to do one of these problems, but actually, right here, is one of those problems. So they're asking us whether or not these two lines are segments, are parallel to each other. And we determine that by creating a proportion and seeing, and really we're asking a question mark, is 90 over 72, is that equal to 50 over 40? And so what I would do, what I'm recommending for you to do, is say 90 over 72, and then reduce that fraction, and then get a particular number, and then reduce this fraction. Do 50 over 40, 50 over 40, and reduce that fraction, and are those two fractions equal to each other? If those two are ratios, right? Fraction and ratio, those really are interchangeable, synonymous terms. So if those ratios are equal to each other, then it tells us for sure that these two lines are parallel. If they are not, if those ratios are not equal to each other, then these two lines, segments, are not parallel. Okay? Go ahead and pause the video and do those two problems, if you would. Oops, actually. And one last little section here. Not only do these principles apply to a triangle in which we have two segments that are parallel to each other, it also applies when we have three lines that are parallel and two transversals. And these two transversals do not have to be parallel. They just have to nothing, really, because what this is really an evolution. I don't know if I use that word, but it's similar, corollary to this case. So here we have two parallel lines, and instead of these two transversals intersecting to create a triangle, think of it as let's open up these two lines, and the same is still true as long as this third line cutting across here is parallel to the other two. Then we can have the same sort of arrangements with the segments. So we're saying that the green over pink equals the blue over the orange. And again, we could do different variations of that. We could also say that the orange over the green, what am I saying, green? Why do I have such difficulty with colors? Orange over the pink equals the blue over the green. We could make that as a proportion if we wanted to. Okay, so for example, from the book here, they want us to be able to find the measure, the length between these two. Now remember, here are your three lines, and what has to be true? What has to be true in order for these three, or for a proportion to be true? It has to be that these three lines are parallel to each other. And they're kind of communicating that to us in a sneaky way. They are saying that angle 1 and angle 2 and angle 3 are congruent to each other. Well, if they are congruent to each other, well, for example, let's look at just these two. If they are congruent to each other, these two are corresponding. So here's your two lines, and then a transversal cutting across those two lines, and these are corresponding to each other. Both of them are up in the top left position. And so if they are congruent to each other, then it tells us that these two lines are parallel. And then same idea down here, that since these two angles, corresponding angles, are congruent to each other, therefore these two lines are parallel. So because these three because these three corresponding angles are congruent to each other, therefore these three lines are parallel. And now that we know that these three lines are parallel, we know that we can set up a proportion with these segments that are created. So in order to find, I think hope they're asking for, let me see, I should slow down and read this. Find the distance HF. Okay, they want us to find this entire distance. Let's just find this smaller distance, GH. That's easier to find, and then we can add that to FG to be able to find it. So let's set up our proportion, and we would say 120 over x equals 150 over 300. Or, if you wanted to get really crazy, and you can do whatever you want to with these things, as long as it kind of is the same kind of pattern. Can I still get this in here and not block my light? We could say x over 300, where is it, equals 120 over 50. See that proportion? X over 300 equals 120 over 150. We could say any of those proportions, and we know that that would be true because these three lines are parallel to each other. And once we solved for x, then we could add that to 120 to get the length of segment HF. And so there you go. You are ready for number 3 now. They want us to find the length of segment AB. So again, you're probably getting bored. You're probably saying, Mr. Evans, I see this. This is so easy. Get out of the way so I can get this done. Well, just fast forward the video then. But we can set up the ratio 16 over 15 equals x over 18, or we could say, if you want to, and this is probably the way I would do it, I want to get the x up in the top left, so I could say x over 16 equals, what is that, 18 over 15. Okay, any kind of a proportion you want to do between these four numbers, as long as it kind of meets this pattern. We have fraction bar equals fraction bar, then cross multiply it and solve for x. You can go ahead and do that. And what's really cool is that not only does this principle apply when I have two parallel segments within a triangle, or three parallel lines and two transversals, it also applies when I have a angle bisector cutting through a triangle. If I have an angle bisector cutting through a triangle, then I have the same principle, the same pattern, same corresponding proportions that are created here. So notice the key here, and that's why I made these in red, so please make that nice and distinct, because none of this would work unless you have know for sure that these two angles are congruent. But once we know that these two angles are congruent, then we know that this is an angle bisector. It is bisecting this larger angle. And then we can say that blue over orange equals green over pink. Or if you wanted to, you could do this rotation kind of thing. And how would you do this here? You'd probably say it like this way. You'd say orange over pink equals, and kind of this way, blue over green. You could do that proportion also. Either one of those arrangements would be correct for creating a proportion or wrinkling your paper if you want to do it. So here we go. With number 4, we want to find the length of AB. So you could set it up this way. You could say 4 square root of 2 over x equals 4 over 4. Well, that's like super dog easy, isn't it? I mean, you could probably do that in your head, wouldn't you? In other words, on the right side, see this ratio? If I was to reduce this ratio, it's going to equal 1. So whatever's up on the top, the underneath is going to be the same thing. So whatever is up on top, underneath is going to be the same thing. So you know what the value of x is, even without having to do any cross multiplication. But go ahead and set up a proportion and do cross multiplication just to demonstrate that that is indeed the case. Or if you wanted to set up the proportion like I normally do, where I wanted the x up in the top left, then how is it going to be? Like this, right? X over 4, here we go, x over 4 equals 4 square root of 2 over 4. And then cross multiply and solve that guy for x. Pretty neat little trick. That it's not a trick. There's nothing trick about this. This is patterns. This is consistency. This will always be the case in all shapes that you create, as long as this is an angle bisector. In other words, as long as these two angles are congruent to each other. All right, have some fun, or at least geometry fun, and then go have some real fun. And I look forward to seeing you in class. Okay, bye-bye.